A parsec sounds like a strange unit, but it is the ruler astronomers use to map the night sky. It sits between the familiar and the unfathomable. A parsec is the distance at which a star shifts 1 arcsecond as Earth moves 1 astronomical unit. That tiny angular change, 1 arcsecond, equals 1/3600 of a degree, a sliver you could barely see with a ruler. Because the angle is so small, the corresponding distance becomes enormous. When you work the numbers, the result is about 3.26 light years. A light year is the path light travels in a year, roughly 9 trillion kilometers. Multiply that by 3¼ and the result matches the kilometer value we assign to a parsec. In kilometers, a parsec measures about 31 trillion. That number dwarfs the distance from Earth to the Moon, which is only 0.384 million kilometers. It also exceeds the span of the solar system, reaching well beyond Pluto's orbit. The origin of the word comes from parallax of 1 arcsecond, a phrase astronomers coined in the 1800s. Early observers tried to measure stellar distances by noting how a nearby star seemed to move against distant ones. They watched the star's apparent shift over a 6-month baseline as Earth traveled around the Sun. The angle they recorded is called parallax, and the distance that gives a 1 arcsecond parallax defines a parsec. If the measured angle is larger, the star is closer. If smaller, it lies farther away. That inverse relationship is why astronomers prefer the parsec. It ties a geometric angle directly to a physical distance. The factor 3.26 appears because a light year is not exactly 1/3 of a parsec. The conversion uses the speed of light and the length of a year, which are not perfectly aligned. When you plug the numbers, 299,792 km/s for light speed and 365.25 days per year, you get roughly 9.46 trillion kilometers. That is the length of 1 light year. Multiply that by 3.26 and the result matches the kilometer value we assign to a parsec. The number feels odd because we are used to measuring in meters or kilometers, not in angles. Our everyday sense of distance comes from walking, driving, or seeing a road stretch ahead. Those experiences involve straight lines, not the tiny tilt of a distant star against a background. I find it hard to picture a triangle that spans the Sun, Earth, and a star 12 light years away. The base of that triangle is 2 astronomical units, about 300 million kilometers. The opposite side stretches over 31 trillion kilometers, a length that dwarfs the base by 8 orders of magnitude. Seeing that ratio in a diagram makes the 1 arcsecond angle look like a whisper of a tilt. When astronomers quote a star's distance in parsecs, they are really stating how small its apparent motion is. A star at 10 parsecs shifts only 1/10 of an arcsecond as Earth circles the Sun. That is far below what the naked eye can resolve. You need a telescope with precise measurement tools. Modern missions like Gaia measure parallaxes to micro-arcsecond precision, pushing distance estimates far beyond the original parsec scale. Those data let us map the Milky Way in 3 dimensions, a task that seemed impossible a century ago. Even with such precision, the basic definition of a parsec remains the same geometric relationship. That constancy gives the unit a sturdy footing amid the shifting numbers of modern catalogs. It also means that when you hear 5 parsecs away, the phrase encodes a specific angle. In principle, you could measure that tiny tilt with a sufficiently precise instrument. That tiny tilt is what ties the human-scale concept of a ruler to the vastness of interstellar space. I don't really know how our brains could naturally relate a half-degree turn of a hand to a 1 arcsecond wobble of a star. The disconnect is why the parsec feels alien, even after you work through the arithmetic. When you step back and compare a parsec to a kilometer, the ratio is staggering. 1 kilometer is what you might drive to the next town. A parsec is the distance to a star that will not move appreciably over a human lifetime. That contrast makes the number feel like a trick of the mind rather than a concrete measure. Nevertheless, the parsec survives because it directly links observation to distance, a link that other units lack. When you hear a galaxy described as a few megaparsecs away, you are hearing a scaled-up version of the same geometric idea. That continuity keeps the unit useful across many orders of magnitude. 1 parsec corresponds to 206,265 astronomical units, the distance from Earth to the Sun multiplied that many times. If you placed the Sun at one end of a ruler and marked a point 206,265 cm away, that point would sit 1 parsec from the Sun. 1 arcsecond is about the width of a human hair seen from a distance of 3 kilometers. Our eyes can resolve roughly 1 arcminute, 1,000 times larger, which explains why the parallax is invisible without instruments. Telescopes equipped with CCD detectors can measure positions down to a few milliarcseconds, pushing the distance ladder further. A milliarcsecond is 1,000th of an arcsecond, a precision comparable to spotting a coin on the moon from Earth. With that level of detail, a star at 100 parsecs shows a parallax of just 10 micro-arcseconds. Micro-arcseconds are 100th of a milliarcsecond, a shift you could not see even with the best ground-based eyes. That is why space missions avoid atmospheric distortion, allowing them to reach that tiny angle. Gaia's catalog now contains parallaxes for over 1 billion stars, each measurement a tiny triangle traced by Earth's orbit. The sheer number of distances lets us see the Milky Way's thin disk, its bulge, and the warp at its edges. All of that rests on the simple geometry of a right triangle, the same shape you learned in school. The right angle sits at Earth, the adjacent side is 1 astronomical unit, and the opposite side is the star's distance. When the angle shrinks to 1 arcsecond, the opposite side equals 1 parsec. That relationship is exact, not an approximation, because it follows from the definition of the angle. It is a rare case where a unit of length is defined by an angle rather than by a physical object. Most everyday units, meters, inches, trace back to a bar of metal or a wave of light. The parsec flips that script, anchoring distance to how we view the sky. That inversion is why the number feels detached from the ground beneath our feet. When I stand on a quiet hill and look up, the stars appear fixed, unchanging. Yet each point hides a minuscule wobble that tells a story of distance. If you could freeze that motion, you would see the sky's true depth. The depth is measured not in meters but in the angle of a shift. That is the essence of the parsec, a bridge built from geometry, not from a ruler. The mount screw clicks once more, aligning the eyepiece with a star that sits 2.3 arcseconds off its catalog position. I stare at the night sky and wonder how we ever claim to know the distance to a point of light that never moves. The trick is not magic, it is geometry, the same kind that a carpenter sketches on a piece of plywood. First, we need a baseline, a length we can measure with confidence. For us, that baseline is the diameter of Earth's orbit around the Sun, roughly 2 astronomical units across. Imagine a straight line drawn from the Sun to Earth in January, then the same line in July, opposite side of the Sun. Those 2 positions of Earth are the ends of the baseline, spaced about 300 million kilometers apart. When we look toward a distant star from each end, the star appears to shift against the far-away background. That apparent shift is called stellar parallax. The angle we actually measure is half the total shift, the angle at the star formed by the 2 lines of sight. We call that tiny angle p, measured in arcseconds. 1 arcsecond is the angle subtended by a 1 centimeter object seen from a distance of about 20 kilometers, a whisper of a turn. Now picture a right triangle. The star sits at the vertex opposite the right angle, the baseline is the side opposite the angle P, and the line from the Sun to the star is the adjacent side. If we drop a perpendicular from the star down to the baseline, we have a clean right-angled shape. The trigonometric relationship is simple. Tan P equals half baseline / distance. Because P is so small, tan P is essentially equal to P when P is expressed in radians. So distance approximately, half baseline P, we usually take the half baseline as one astronomical unit, the mean Earth-Sun distance. Replace P with 1 arcsecond, convert that to radians, approximately 4.848 times 10, and the distance works out to about 265 astronomical units. That length is defined as 1 parsec, short for parallax second. In other words, a star 1 parsec away will shift by exactly 1 arcsecond as Earth travels from one side of its orbit to the other. If the shift is smaller, the star lies farther. If larger, it is nearer. The math is clean, but the picture is harder to hold. I find it hard to picture a triangle that stretches across a vacuum so empty that no ruler can reach it. The only thing we can grip is the baseline, the orbit we have mapped with probes and radio waves. Everything else is inferred from that tiny angle. To make the idea more concrete, I often hold my thumb out at arm's length. When I close one eye, the thumb appears against a distant wall. Opening the other eye makes the thumb shift slightly. The shift mimics the stellar parallax, the wall standing in for the distant background of galaxies. If I move my head a few centimeters, the thumb's apparent motion is easy to see, even though the angle is only a few degrees. Scale that motion down by a factor of 1,000,000, and you have the parallax of a star a few parsecs away. The analogy is imperfect. My thumb is only a few centimeters, not a star billions of kilometers across, but it captures the geometry. In the lab, we would place a ruler on a table, look at a distant object, then move the ruler sideways and note the change in apparent position. Stellar parallax is the same experiment, only the ruler is Earth's orbit and the distant object is a sun-like sphere many light-years away. Astronomers record the star's position at 6-month intervals, then fit the data to a sinusoidal curve. The amplitude of that curve gives the parallax angle. Because the Earth's orbit is not a perfect circle, corrections are applied, but the basic triangle remains. The right triangle construction also explains why the parallax method fails for most stars. Beyond a few hundred parsecs, the angle drops below the resolution of even the best telescopes, and the triangle collapses into a line we cannot measure. That limitation pushed astronomers to develop other distance ladders, but the parsec still anchors the whole system. When I calculate a distance, I write the equation in my notebook. D equals 1 AU/tan P, and then I replace tan P with P radians because P is so small. It feels almost lazy, but the approximation is justified by the numbers. If P equals 1, then P radians approximately 4.848 times 10, and D approximately 1 AU/4.848 times 10, approximately 265 AU. That number, 265, is the conversion factor between arcseconds and astronomical units. It is a strange bridge between angular measurement and linear distance, forged by geometry alone. I sometimes wonder whether the ancient Greeks, who first imagined triangles in the sky, ever considered that a single second of arc could encode a distance measured in billions of kilometers. Their tools were far cruder, yet the same right triangle logic would have applied. Modern instruments add layers of precision CCD detectors, adaptive optics, but the underlying shape stays the same. Even the most sophisticated space missions still rely on the Earth's orbital baseline to define the parsec. A subtle point: the baseline is not the full diameter of the orbit but the radius, because the parallax angle is defined from the sun's perspective to one side of the orbit. If we mistakenly used the full diameter, we would double the angle and have the derived distance. That error would be easy to make, yet the community has settled on the 1/0 convention for decades. When I look at the raw data, a star's right ascension and declination measured months apart, the shift is often a few milliarcseconds, invisible to the naked eye. Yet those few thousandths of a degree translate to dozens of parsecs, a reminder of how tiny angles can span enormous spaces. The math does not lie, but my intuition sometimes rebels. It doesn't quite make sense when you say a point of light moves less than a hair's breadth on a screen, yet sits billions of kilometers away. The right triangle picture helps, but I still feel a little uneasy, as if the universe is whispering a secret that my ruler can only catch in fragments. One practical tip for students: draw the triangle on graph paper, label the baseline as 1 AU, mark the angle P, and then use the small angle approximation to compute the hypotenuse. Seeing the numbers on paper makes the abstraction less oppressive. If you tilt the paper, the triangle seems to lean, reminding you that the real configuration lives in 3 dimensions, not a flat sheet. Even the simplest trigonometric derivation hides a subtlety. The star's own motion through space can masquerade as parallax if observations span many years. Astronomers correct for that by measuring proper motion separately, but the core geometry remains unchanged. In the end, the parsec is a unit born of a triangle, a baseline, and a minuscule angle. It is a reminder that distance can be expressed without ever laying a tape measure across the void. The next time I raise my thumb against the night sky, I will notice how the tiny shift feels like a whisper of geometry, a single arcsecond echoing across the darkness. A faint tremor in my eye muscles, barely perceptible, marks the point where Earth's orbit meets the distant star's silent line. I stare at the ancient sky charts like a tired technician checking a worn-out gauge. The earliest astronomers, Hipparchus among them, had only a simple sighting tube and a wooden armillary. They measured the angle between a bright star and the sun at the moment of greatest elongation, hoping the geometry would give them the Earth-Sun distance. The numbers they wrote down were crude, yet the method already implied a ratio of lengths they could not directly see. Hipparchus' estimates of the solar parallax hovered around a half degree, a value that today would be off by a factor of several thousand. He recorded his observations on papyrus, the ink drying under the same sun he tried to measure. The process felt like trying to weigh a grain of sand with a kitchen scale. I find it hard to picture how they trusted those angles when the instrument itself could wobble with a breeze. Centuries later, the idea of parallax resurfaced, but the tools had changed. By the early 19th century, astronomers had built fine filler micrometers that could split the image of a star by a fraction of a millimeter. Friedrich Bessel, standing at the Königsberg Observatory, pointed his telescope at 61 Cygni and recorded its minute shift against distant background stars. The shift was only 0.3 arcseconds, less than the width of a human hair seen from a kilometer away. When Bessel announced the first successful stellar parallax in 1838, the scientific community held its breath. The result was a distance of about 10 light-years, a number that seemed absurdly small and absurdly large at the same time. Bessel's work relied on painstaking visual timing. He noted the exact moment a star crossed a reticle wire, then repeated the measurement months later. The human eye, however, is a noisy detector. The recorded angles jittered with each breath. The precision limit was set by the observer's steadiness and the telescope's optics. In the lab note style of the era, the margin of error was written in the margin, a reminder that the numbers were not absolute. The next leap arrived with the invention of photographic plates. By the late 19th century, Astronomers could expose a glass plate for several minutes, imprinting the star field with a permanent record. The plates captured the same star at different epochs, allowing a direct comparison of positions without relying on a human's fleeting judgment. The technique reduced random eye errors but introduced new ones. The emulsion's grain, the uneven development, the slight warping of the glass. Still, the ability to stack multiple exposures and average the result pushed the precision down to a few hundredths of an arcsecond. Space-based astrometry finally lifted the whole experiment above the turbulent atmosphere. The Hipparcos satellite, launched in 1989, carried a modest telescope that scanned the sky while orbiting Earth. Its detectors measured stellar positions with milliarcsecond accuracy, a scale that would make the earlier ground-based errors look like clumsy scribbles. The data stream was a continuous flow of photon counts, each photon a tiny tick in a massive clock. The satellite's attitude control system kept the instrument pointed within a fraction of a degree, a feat that felt like balancing a feather on a moving train. Yet even Hipparcos hit a wall. The instrument's baseline, the distance between its two viewing fields, limited the smallest angle it could resolve. To improve further, astronomers turned to interferometry, a method that combines light from separate telescopes to synthesize a larger aperture. By spacing two mirrors tens of meters apart and measuring the interference pattern of incoming starlight, the effective resolution can reach microarcsecond levels. The Very Large Telescope Interferometer, VLTI, and the CHARA array now achieve such precision on bright nearby stars, turning the sky into a laboratory of fringes and phases. Interferometric measurements demand extreme stability. The mirrors must sit on vibration-isolated platforms, the air temperature controlled to within a fraction of a degree, the laser metrology system constantly checking the distance between the mirrors down to nanometers. A tiny thermal expansion of a support strut can shift the fringe pattern enough to masquerade as a false parallax signal. The data reduction pipelines are filled with correction terms that read like a list of every possible disturbance, a reminder that we are still wrestling with the same fundamental limits that haunted Hipparchus, only in a different language. The limits of precision today are set not only by instrument design, but also by the intrinsic variability of the stars themselves. Many stars wobble due to unseen companions, surface convection, or magnetic activity. Those motions add noise to the astrometric signal, blurring the clean geometric picture we hope to obtain. In the lab note entries of modern surveys, the error bars often include a term labeled astrophysical jitter, a concession that the universe does not always cooperate with our measurements. Space-based interferometry has been proposed, promising baselines of hundreds of meters free from atmospheric turbulence. The concept would place multiple spacecraft in formation, each acting as a collector, their distances measured by laser ranging. The idea is tantalizing, but the engineering challenges feel like trying to keep three hummingbirds in perfect formation while they each carry a delicate mirror. We don't really know whether the technology will ever be robust enough for a long-term mission. Looking back, the thread that ties Hipparchus to modern interferometers is a stubborn desire to turn angles on the sky into lengths we can write down. Each generation added a tool that reduced one source of error while exposing another. The ancient angle estimates were limited by the naked eye. Bessel's visual timing was limited by human steadiness. Photographic plates added grain. Space telescopes removed atmospheric blur but introduced spacecraft jitter. Interferometry pushes the baseline to the edge of engineering tolerances. The progression reads like a series of lab notes, each entry marked with a new source of uncertainty. Even as we push toward microarcsecond precision, the fundamental geometry remains unchanged. A parallax angle of 1 arcsecond still corresponds to a distance of 1 parsec, a definition that has survived for 2 centuries. The number feels abstract, yet when I look at the interferometric fringe pattern on a monitor, I see a series of bright and dark bands, each band a whisper of the star's position shifting by a fraction of a nanometer. It is a reminder that the distance we are trying to capture is not a static line, but a subtle dance of light and motion. The last entry in my notebook today records a fringe shift of 0.8 nanometers on a baseline of 130 meters, corresponding to a parallax change of 0.4 microarcseconds for a nearby red dwarf. The value sits on the edge of the instrument's noise floor, a tiny ripple that could be swallowed by a stray thermal pulse. I close the notebook, noting the temperature of the lab at 21.3 degrees C and the faint hum of the cooling system that keeps the detectors cold. The observation ends not with a conclusion, but with the faint, steady tick of the laser metrology system, marking each millimeter of baseline as it expands and contracts in the quiet. The parsec first entered my notebook as a stubborn conversion, 3.26 light years, a distance that stubbornly refuses to shrink in everyday speech. I still hear the echo of that number when I stare at the Milky Way's faint band, trying to imagine a ruler that stretches across half a galaxy. It feels absurd, and yet it is the only unit that lets us lay the spiral arms out like the spokes of a tired wheel. When we talk about the galactic disk, the first number that comes up is its thickness. Roughly 300 parsecs, give or take a few dozen. That is the distance from the mid-plane to the top of the star-filled layer, measured not in miles or kilometers, but in a unit that ties directly to the way we measure stellar motion. The disk is not a perfect pancake. It flares outward, and the thickness varies with radius, but the parsec gives us a single scale to compare those variations. I find it hard to picture a sheet of paper that thick, even when I stretch my hand across a kitchen counter. Nearby stars provide the anchor points for the whole map. Within 1,000 parsecs of the Sun, we have reliable parallaxes, the tiny wobble of a star's position caused by Earth's orbit. Those wobbles translate directly into distances measured in parsecs. Because the definition of a parsec is exactly the distance at which 1 astronomical unit subtends 1 arcsecond. The dataset feels like a scatter of pins on a corkboard, each pin labeled with a number that tells us how far the pin lies from us. The distribution of those pins is not uniform. We see clusters where star-forming regions sit, and gaps where interstellar clouds block our view. Those clusters line up along the spiral arms, the grand arcs that wind around the galactic center. To trace an arm, we start at a known point, say the Orion spur where the Sun lives, then step outward in increments of a kiloparsec, 1,000 parsecs, following the pattern of young, massive stars and giant molecular clouds. The kiloparsec becomes a convenient stepping stone, a larger yardstick that lets us jump from one segment of an arm to the next without losing the sense of scale. It is a bit like measuring a road in miles rather than feet. The numbers feel manageable, the picture stays coherent. Mapping the arms is not just about drawing lines, it feeds into our understanding of galactic dynamics. The rotation speed of the disk varies with radius, and that variation depends on how mass is spread out. If we misjudge distances, the inferred mass distribution will be off, and the derived rotation curve will mislead us about the presence of dark matter. By anchoring every point on the curve to a distance expressed in parsecs, we keep the geometry honest. I sometimes wonder whether the choice of units subtly shapes the equations we write, but the math insists on consistency regardless of our preferences. The relation between parsecs and kiloparsecs also helps us compare the Milky Way to other galaxies. External spirals are measured in kiloparsecs from the outside, their arm pitch angles expressed in degrees per kiloparsec. When we translate our own arm measurements into the same language, we can ask whether the Milky Way is a typical spiral or an outlier. The answer hinges on the same parsec-based distances that we use to chart the positions of nearby Cepheid variables, those pulsating stars that act as standard candles. Their periods give us luminosities, and their apparent brightness tells us how far away they sit, again in parsecs. Even the thickness of the disk feeds back into the dynamics. A thicker disk implies a higher vertical velocity dispersion among the stars, which in turn suggests a different history of heating events, perhaps past mergers or spiral arm scattering. By measuring that thickness in parsecs at various radii, we can sketch a profile of how the disk has been stirred over billions of years. The profile is a series of numbers, each tied to a parsec scale, and each telling a subtle story about the forces that have acted on the Milky Way's stellar population. There is a practical side to all this that often gets lost in the poetry of spiral arms. Telescope time is allocated in blocks, and each block must be justified with a clear target list. Those targets are chosen because we know their distances in parsecs, which determines how bright they will appear and whether a given instrument can resolve them. The planning sheets are full of columns labeled dist PC and dist KPC, and the whole schedule hinges on those numbers being right. A misestimated distance can waste hours of observation, and the cost of that mistake is measured in both time and money. When we finally lay the map on a screen, the spiral arms appear as faint, curved ribbons of colored points, each point a star whose distance we have pegged to a parsec or a kiloparsec. The colors often encode age or metallicity, but the underlying grid is purely geometric, built from the parsec ruler. The image is both beautiful and stark. It reminds me that the grandeur we see is assembled from countless tiny measurements, each one a small, stubborn number. I sometimes stare at the edge of the map where the data thin out, where the last reliable parallax sits at about 8,000 parsecs, and wonder what lies beyond the reach of our current instruments. The parsec still holds its place, but the farther we push, the more we rely on indirect methods, redshift, standard candles, statistical models. Those methods still report distances in kiloparsecs, but the uncertainty grows and the picture blurs. It doesn't quite make sense when you say it aloud. A unit designed for nearby stars stretched to the galaxy's edge. The last thing I notice before turning off the screen is a tiny, bright dot labeled Barnard star, 1.82 PC. It sits in the corner, a reminder that even the closest stellar neighbor is measured in the same units we use for the galaxy's grandest structures. The dot flickers, and the number stays stubbornly precise. I stare at the old chart on my desk, the thin lines of light years turned into numbers that end in PC. The unit feels like a ruler that has been stretched beyond the edge of our own spiral, into the faint glow of distant galaxies. It is odd that a distance once defined by a nearby star now measures the space between us and objects we can barely resolve. When I first measured a Cepheid variable in the Andromeda galaxy, the star's pulsation gave me a period, and the period gave me an intrinsic brightness. The math was simple. Compare that brightness to what we see, and the difference tells you how far the light has traveled. The result was a distance of about 780 kiloparsecs, a number that still feels too large to fit on a sheet of paper. I find it hard to picture a line that long. It would have to stretch across the whole laboratory and keep going. Cepheids are the first rung on the cosmic distance ladder I use. Each rung is a calibration step, a way to reach higher. After Cepheids, I turn to type Ia supernovae, exploding white dwarfs that shine with almost identical peak luminosities. Those are called standard candles because their brightness is predictable. When a supernova flashes in a galaxy 10 megaparsecs away, its light arrives dimmer, and the dimness translates into a distance in megaparsecs. The conversion is just a scaling of the same parsec definition, but the numbers become millions instead of thousands. The ladder does not rise without friction. Each step introduces uncertainty, a grain of error that accumulates. I sometimes hear a faint hiss in the data, like static on an old radio, reminding me that the calibration of one rung depends on the previous one. If the Cepheid period luminosity relation is off by 1%, every supernova distance above it shifts by the same fraction. I don't really know how many hidden biases linger in the dust of distant galaxies. Redshift adds another layer. Light from a galaxy that is receding stretches, shifting its spectrum toward longer wavelengths. The amount of shift, called Z, is measured by the displacement of known spectral lines. In the nearby universe, the shift is small, and the recession speed is roughly proportional to distance. That proportionality is Hubble's law. V equals h0 times d, where d is expressed in megaparsecs. The constant h0 is the rate at which the universe expands today. When I plug a measured redshift into the law, I get a distance in megaparsecs, independent of any candle. The two methods, standard candles and redshift, often meet. A supernova in a galaxy with a known redshift provides a cross-check. If the candle says 150 mpc and the redshift says 155 mpc, the agreement is reassuring. When they disagree, I feel a pressure, like a scale tipping under a hidden weight. Sometimes the mismatch points to an error in the assumed Hubble constant. Other times it hints at something deeper in the fabric of space. Hubble's constant itself is a source of quiet debate. Different teams measure it with Cepheids and supernovae, getting around 73 km s/mpc, while others use the cosmic microwave background to infer about 67 km s/mpc. The discrepancy is small in everyday terms, but over billions of parsecs it translates into a noticeable shift in the age of the universe. I find it hard to picture how a few kilometers per second per megaparsec can change the story of everything. The distance ladder also reaches into the realm of dark energy. The accelerated expansion of the universe was first noticed by comparing supernova distances to redshifts. If the universe were expanding at a constant rate, the supernova brightness would follow a simple curve. Instead, the curve bends, indicating that distant supernovae are dimmer than expected. That dimness implies the expansion has sped up, a phenomenon attributed to dark energy. The measurement hinges on the parsec scale. Every megaparsec of distance adds a tick on the clock that tells us how fast space is stretching. To extract the acceleration, I plot the distance modulus, essentially the difference between observed and intrinsic brightness, against redshift. The slope of that plot encodes the influence of dark energy. The numbers are delicate. A shift of a few hundredths of a magnitude can swing the inferred equation of state of dark energy. The whole analysis rests on the reliability of the parsec ladder, on the assumption that a type Ia supernova truly is a standard candle across cosmic time. There are ways to test that assumption. One method looks at supernovae in galaxies where Cepheids have already given a distance. By comparing the two, I can see whether the supernova's peak brightness changes with the host galaxy's metallicity or age. So far, the variations are small, but the data are noisy. I sometimes hear the faint clatter of statistical fluctuations, like a distant train rattling on tracks, and I wonder whether we are missing a subtle systematic effect. Even the redshift distance relation is not immune to complications. At higher redshifts, the simple linear form of Hubble's law breaks down. The universe's expansion history, shaped by matter and dark energy, bends the curve. To translate a redshift of 0.5 into a distance, I must integrate the Friedmann equations, assuming a cosmological model. That integration returns a comoving distance measured in megaparsecs, a number that tells me how far the light has traveled in the expanding fabric. The model itself contains parameters that we infer from the same distance measurements, a circularity that always makes me uneasy. In practice, I use software that takes a redshift, plugs in a set of cosmological parameters, and spits out a distance in megaparsecs. The output is precise to many decimal places, but the underlying assumptions are rough. The software does not convey the cold feeling of uncertainty that sits behind each digit. I sometimes stare at the screen and hear the faint hum of the computer's fan, a reminder that the numbers are only as good as the model we feed them. The scale of a megaparsec is hard to feel. 1 megaparsec equals about 3 million light-years, a stretch that would swallow the entire local group of galaxies. If I were to lay a ruler from the Milky Way to the Virgo cluster, it would be over 20 megaparsecs long, a distance that dwarfs the size of any human-made structure. The sheer size makes the parsec feel less like a unit and more like a concept we use to keep the universe in check. When I write a note about a galaxy at 100 mpc, I imagine the light traveling through intergalactic space for 326 million years, crossing regions of tenuous gas, feeling the faint pressure of the cosmic web. The photons arrive at my telescope, cold and ancient, and I translate their arrival into a number that fits on a spreadsheet. The translation process is a series of approximations, each adding a layer of abstraction. I have learned to accept that some of the distance measurements will always carry a margin of error that feels like a grain of sand slipping through my fingers. The error bars are not just statistical. They embody the unknowns of stellar evolution, the geometry of space, and the physics of dark energy. When I look at a plot of distance versus redshift, the scatter of points feels like a whisper of the universe's complexity. Sometimes I pause and think about the original definition of a parsec, the distance at which one astronomical unit subtends an angle of 1 arcsecond. That definition is rooted in geometry, in the simple idea of a triangle. Yet the triangles we draw now span billions of light-years, their corners placed on stars we cannot touch. The definition remains exact, but the application stretches it to its limits. In the end, the parsec and its larger cousin, the megaparsec, are tools that let us map the universe's expansion. They turn faint glimmers into a scaffold we can study, a scaffold that supports our attempts to understand dark energy, the age of the cosmos, and the fate of everything beyond our own galaxy. I close the notebook, feeling the paper's grain under my fingertips, and notice a stray dust mote drifting across the window, catching the late afternoon light. A parsec sits at the edge of my everyday map. It is 3.26 years of light, a stretch that feels abstract. I try to replace that light-years-long ribbon with a road trip. Driving to the moon takes about 3 days, a distance most of us have heard. Now imagine extending that trip 1,000 times, then 1,000 more. The result still falls short of a single parsec. I find it hard to picture a line that long on any highway. If a football field is a familiar unit, stacking them helps. One field measures about 100 meters. A parsec would need billions of them. Picture a stadium roof, then another and another, filling the horizon. The stack would rise beyond any weather-worn roof we have ever seen. Even the tallest skyscraper, a few hundred meters, is a speck in that pile. Turning to Earth size, the planet spans about 0.000015 parsecs. That means you could line up about 4 million Earth diameters across 1 parsec. Seeing that many spheres stacked in a line feels like a thought experiment gone wild. The light that travels those 3.26 years leaves Earth as a pulse of photons. By the time it reaches the far end of a parsec, the sun has already set many times. I don't really know how to feel the weight of that delay. It's not a distance you can walk or even drive in a lifetime. Even a generation of rockets would only scratch the surface of a parsec. When I try to translate that into a familiar picture, the numbers blur. The moon is 384,000 kilometers away. A parsec is about 30,857,000,000,000 kilometers. That ratio is roughly 81 million to 1. If you could drive a car at 100 km/h, you would need 8 million years to cover a parsec. My mind stalls when I try to imagine a road that long. The feeling is similar to looking at a grain of sand and trying to see the beach beyond. A parsec is a grain in the vastness of the Milky Way, yet a beach for our senses. When I tell a friend that a star 10 parsecs away is about 33 light-years distant, the eyes glaze. The numbers become a kind of abstract music, not a tangible road. I sometimes think of a parsec as a stretched rubber band, thin but endless. Pulling it tighter only makes the distance more obvious, yet still invisible. The emotional impact of such a scale can feel like a quiet awe. It is not the fireworks of a supernova, but a slow, steady breath. That breath is measured in years, not seconds, and it stretches beyond a human lifetime. If you place a clock on the far side of a parsec, its ticks would seem alien. The ticking would be a reminder that even light, our fastest messenger, obeys a slow schedule. I sometimes wonder whether our language can ever truly capture that slowness. We use numbers, but numbers feel thin when stretched across such emptiness. A parsec is a bridge between the human habit of counting and the universe's vastness. When I stand on a quiet hill and watch the night, the stars seem close. In reality, each point of light sits many parsecs away, a reminder of hidden depth. I feel a small tug of humility, like a gentle tug on a rope. The rope is our imagination, stretched thin over a parsec-long gap. When it snaps, we are left with the quiet echo of numbers. I find it hard to picture the exact moment that echo fades. Perhaps the best we can do is keep the echo in mind, a faint reminder. That reminder can sit on a desk, a small card with the numbers written. Seeing 3.26 years next to 1 parsec feels like a tiny compass needle pointing outward. The needle does not tell us the whole journey, only the direction. If I were to write a note to my future self, I would include the football field stack. It would read, "Imagine a field, then imagine it repeated until the horizon disappears." That image stays with me longer than any raw number. When I think of a parsec, the feeling is less about size and more about patience. Patience is something we practice on Earth, in traffic, in lines, in waiting for rain. Applying that same patience to a parsec feels both absurd and oddly appropriate. When I catch myself measuring the distance to the grocery store in Earth diameters, just for fun, it makes the world feel a little larger, but the parsec still looms. The looming is not threatening. It is simply a reminder of scale beyond our daily chores. I don't really know if that feeling helps us navigate the universe, but it steadies the mind. When the night sky clears, I can see a few bright points that are many parsecs away. Each point carries a story measured in years of travel, a silent messenger. I imagine those messengers as tiny postcards, stamped with a date from a distant past. The stamp reads 3.26 years, and the address is a star we cannot reach. That image stays with me as I turn off the lamp and stare into the dark. A single dust mote on the windowsill catches the light, reminding me of the tiny scales we handle daily. The windowsill is only a few centimeters away, yet the parsec stretches beyond the glass. I notice the faint line where the glass meets the frame, a small boundary. That boundary feels like the edge of a parsec, thin and barely perceptible. If I line up the football fields edge to edge, the line would cross continents before disappearing. Crossing a continent takes hours, but crossing a parsec would take millions of such trips. I can feel the fatigue in that thought, like a long hike without rest. The hike analogy helps me keep the distance grounded, even if the numbers stay abstract. When I think of the light travel time, I picture a slow train moving through darkness. The train's whistle would echo for 3 years before reaching the next station. That echo would be a faint hum in the background of the universe. I find it hard to hear a hum that never reaches my ears. The notion of waiting 3 years for a single photon feels both absurd and intimate. Intimate because it connects us to events that happened before we were born. It is a reminder that our lives are just a blink in the timeline of a parsec. When I step outside on a cold night, the air feels thin, like the space between stars. But the thinness of air is nothing compared to the emptiness that a parsec contains. Even the vacuum holds a few particles per cubic meter, a trace of matter. That hush is still far louder than the silence we imagine across a parsec. I sometimes wonder whether the emptiness itself has a texture we cannot sense. Perhaps it feels like the smoothness of a polished stone, unseen until you touch it. We cannot touch a parsec, but we can touch the idea of it like a cold metal bar. The bar is cold because it reminds us of the distance, not because of temperature. When I think of the bar, I feel a slight shiver in my fingertips. That shiver is the only physical sensation I can attach to a parsec. It is a small bridge between mind and number, a fleeting pulse. I leave the room and the lamp flickers, casting a thin line on the wall. The line looks like a horizon, a reminder of the edge we cannot cross. I notice the dust particle caught in that line, suspended like a star caught in a parsec. The parsec sits in the back of the mind like a weight you never quite lift. It is a distance, yet it is defined by an angle, an arc of a tiny triangle drawn across the sky. When I first heard a colleague say 3 parsecs away, the word sounded like a joke, a riddle that refused to settle into a straight line. I find it hard to picture a length that is born from a sliver of tilt. Our brains grew up measuring the world with our hands, our feet, the stretch of a rope. Those are linear tools. They give us a sense of here to there that feels solid. Angles, on the other hand, belong to a different sense, one that lives in the turn of the head, the sweep of a gaze. The brain treats a degree as a direction, not a stretch of road. When the definition of a parsec mixes the two, the mental picture collapses. Scale invariance adds another layer. In everyday life, we can zoom in on a table and still recognize it as a table. The same shape repeats at different sizes. The sky, however, does not obey that habit. A star 10 light-years away shifts its position by a fraction of an arcsecond, a number that feels like a whisper compared to the roar of a kilometer. The mind resists translating that whisper into a kilometer-scale distance. Education often cements the problem. Textbooks introduce the parsec as the distance at which one astronomical unit subtends 1 arcsecond. The sentence is precise, but it is also abstract. Students hear 1 arcsecond and picture a tiny line on a ruler, not the minuscule angle formed by Earth's orbit seen from a distant star. The language itself becomes a barrier. The unit parsec carries a history that does not match our everyday vocabulary. It sounds like a foreign word, and the brain treats foreign words as less trustworthy. I have sat in a lecture hall watching a professor write 1 PC equals 3.26 Li on a blackboard. The symbols are neat, the numbers exact, yet the room feels empty. The audience nods, but the mental model remains vague. It doesn't quite make sense when you say it aloud. 3.26 light-years per parsec. The phrase rolls over the tongue, but the picture in the head stays hazy. Scientists have learned to sidestep the confusion by anchoring the parsec to familiar experiences. One method is to compare the angle to the width of a human thumb held at arm's length, about 2 degrees. An arcsecond is 1/3600 of that. By shrinking the reference down, the brain can grip the tiny angle. Then the distance follows. If that tiny angle corresponds to the Earth-Sun separation, the line to the star stretches for many trillions of meters. The trick is to let the mind walk from a familiar tilt to an unfamiliar stretch. Another strategy is to use physical models. A simple yardstick placed a few meters away can cast a shadow that mimics the parallax of a nearby star. When the shadow moves a fraction of a millimeter as the yardstick is shifted, the observer can feel the shift. The feeling of the tiny motion grounds the abstract angle in a tactile sense. I have watched students lean forward, eyes narrowed, trying to see that barely moving line. The tension in their shoulders tells me the concept is finally reaching them. Language can be reshaped too. Instead of saying parsec, some educators prefer parallax second. The extra word reminds the listener that an angle is involved. When the term is broken into its parts, the brain has a chance to rebuild the idea piece by piece. I have heard a colleague whisper parallax second in a hallway, and the person on the other end paused, as if the phrase had nudged a dormant connection. Even the choice of units matters. Light years are easier to imagine because they are tied to the speed of light, a constant we can feel in everyday technology. Lasers, fiber optics, the glow of a screen. By first converting a parsec into light years, then into the time it would take a photon to travel, the distance becomes a story of travel, not a static number. The narrative of a photon's journey gives the brain a motion to follow, which feels more natural than a static angle. Scale invariance can be turned into an advantage. When we look at the Milky Way's spiral arms, we see patterns that repeat at many scales. By pointing out that the same geometry that shapes a pine cone also governs the distribution of stars, we remind the mind that angles and distances are not strangers. The brain, accustomed to patterns, can accept the parsec as another instance of a familiar rule. I do not claim these tricks erase every doubt. We don't really know how many neurons fire when a student finally says, "I get it." The moment is fleeting, and the brain may revert to the old shortcut of treating everything as linear. Yet the repeated use of concrete analogies seems to push the barrier back, even if only a little. In practice, researchers often bypass the parsec altogether, reporting distances in kiloparsecs or megaparsecs when the numbers become large. The shift to larger units reduces the need to think about the tiny angle. The mind can focus on the scale of the galaxy instead. It is a pragmatic compromise: accept the paradox, then hide it behind a bigger number. When I write a paper, I still include the definition of a parsec in the footnote. It feels like a reminder to the reader that somewhere, an angle is doing the heavy lifting. I watch colleagues glance at the note, then move on, trusting that the community has collectively built a mental scaffold. The scaffold is shaky, but it holds enough weight to let us calculate orbital periods, map dark matter, and plan interstellar probes. One classroom experiment that sticks with me involves a simple protractor and a flashlight. The flashlight represents a distant star. The protractor's small opening mimics the parallax angle. By rotating the protractor just a fraction of a degree, the beam moves across a distant wall, tracing a line that grows longer the farther the wall is placed. The visual of a tiny turn creating a huge shift on a far surface mirrors the parsec's definition. The students' faces light up when the wall's distance is measured in meters, then converted to astronomical units, then to parsecs. The chain of conversions feels like a ladder they can climb, rung by rung. Even after the lesson, the word parsec can still sound like a misprint. That is why many astronomers use the abbreviation PC in casual conversation, as if the mystery were a small typo. The shorthand does not solve the mental mismatch, but it reduces the friction of saying a word that feels foreign. Over time, the abbreviation becomes a familiar sound and the brain stops balking at it. I sometimes sit at night, looking up at a star I know is about 4 parsecs away. The point of light is no larger than a grain of sand against the dark. I try to imagine the Earth's orbit as a tiny baseline, the star's position shifting by a sliver of an arcsecond as we move around the sun. The image is faint, like a whisper in a cold room. It does not fill the mind, but it stays there, a quiet echo. The paradox remains, a distance defined by an angle that our senses treat as direction, not length. Scientists keep moving forward by turning that angle into a story, a model, a tactile experience. The brain, stubborn as it is, can be nudged, if only a little, to accept the strange conversion. A colleague once told me that the best way to remember a parsec is to picture the tiny tilt of a ruler held at arm's length, then to feel the weight of a galaxy in your hands. I have never quite felt that weight, but I can hear the faint click of the ruler's edge against my thumb, and it is enough for the moment. The Gaia spacecraft has been scanning the sky for more than a decade, its twin telescopes tracing the faintest points of light with a patience that feels almost mechanical. Each rotation deposits a handful of photons on a CCD, and the onboard processor extracts a centroid that is later compared with billions of others. The result is a catalog where the positions of more than 1 billion stars are known to within a few dozen micro-arcseconds, a distance so small it would be the width of a human hair seen from 100 kilometers away. I keep a notebook of the error budget, and it reads like a list of tiny annoyances. Thermal fluctuations in the payload cause the mirrors to expand by a few nanometers, shifting the focal plane just enough to introduce a bias of several micro-arcseconds. The attitude control system, while precise, still jitters at the level of a few milliarcseconds per hour, and that jitter must be modeled and removed. Radiation damage to the CCDs creates charge transfer inefficiency, subtly smearing the image and forcing a correction that depends on the star's color and brightness. Each of these effects is measured, calibrated, and subtracted, but the residuals remain a stubborn background. When the first Gaia data release arrived, I stared at the Parallax histogram and felt a strange mix of excitement and disbelief. The median formal uncertainty for bright stars sat at about 20 micro-AS, yet the scatter in the residuals hinted at systematic patterns across the sky. It didn't quite make sense when you say it aloud. A spacecraft orbiting 1.5 million kilometers from Earth can claim a distance precision that would let us weigh the thickness of a sheet of paper on the moon. The reality is that the numbers are only as trustworthy as the models that correct them. Very long baseline interferometry, or VLBI, offers a complementary route to the same goal. By linking radio telescopes across continents, VLBI creates an effective aperture the size of Earth, turning the planet itself into a gigantic dish. The technique measures the delay between the arrival of a radio wave at each antenna to a fraction of a nanosecond, which translates into an angular precision of a few micro-arcseconds. Unlike Gaia's optical sensors, VLBI works at radio frequencies, so it can target quasars, masers, and the handful of radio-bright stars that Gaia cannot see. In the lab, we often compare the two methods by looking at sources that appear in both catalogs. The positions of a handful of CO maser stars, measured by VLBI, line up with Gaia's optical coordinates within 30 micro-AS after applying a global rotation. That agreement is encouraging, but it also reveals a mismatch in the reference frames. The radio frame is defined by distant quasars assumed to be fixed, while Gaia's frame is anchored to the same set of quasars observed in the visible. Small offsets between the two frames linger, and they must be solved before we can claim a truly universal astrometric grid. Micro-arcsecond challenges are not just technical, they are statistical. When you push uncertainties down to the level of a few parts per million, the assumptions of Gaussian error distributions begin to break down. Outliers, cosmic rays, stray light, unexpected spacecraft motions carry disproportionate weight. I have spent evenings fitting robust estimators to the parallax data, only to find that the choice of prior can shift the inferred distance by several percent for the most distant objects. It feels like trying to hear a whisper in a room full of humming machinery. The impact on stellar astrophysics is immediate. Accurate distances let us convert apparent magnitudes into absolute luminosities without the usual fudge factor of average extinction. For Cepheid variables, the period luminosity relation becomes a tighter ruler, and the calibration of the Hubble constant tightens in step. Open clusters that once sat at ambiguous distances now line up neatly along a single isochrone, allowing us to test models of stellar rotation and mixing with unprecedented fidelity. Even the faintest red dwarfs, whose parallaxes were previously uncertain by tens of percent, now have distances known to within a few percent, opening a clearer view of the low mass end of the mass-luminosity relation. I find it hard to picture the scale of the improvement. A star at 1 kiloparsec with a 10 micro-AS parallax has an uncertainty of only 0.01 pc, roughly the distance between a house and a neighbor's garden. That level of precision turns the Milky Way into a three-dimensional map where individual spiral arms can be traced as if they were painted on a wall. The distribution of dark matter, inferred from stellar motions, can be probed with a granularity that was previously reserved for simulations. It doesn't feel like a leap. It feels like a slow, deliberate tightening of a knot. Future missions promise to push the envelope further. The planned space interferometer, though still in concept, aims to achieve sub-micro arcsecond astrometry by forming interference fringes between separated telescopes in orbit. On the ground, upgrades to the VLBI network, adding new dishes in Africa and Antarctica, will fill gaps in the baseline coverage, reducing the systematic errors that arise from uneven antenna distribution. The combination of optical and radio techniques may eventually produce a hybrid reference frame with uncertainties below 5 micro-arcseconds across the entire sky. There are still unknowns. The effect of solar radiation pressure on the spacecraft's attitude control is not fully modeled at the micro-arcsecond level, and the long-term stability of the optical bench under micrometeoroid impacts remains an open question. We don't really know how much the interstellar medium's scattering will bias radio positions at the highest frequencies. These gaps remind me that each gain in precision uncovers a new layer of subtlety. One practical breakthrough I have watched emerge is the refinement of stellar ages for the nearest solar analogs. By combining Gaia parallaxes with asteroseismic frequencies from space telescopes, researchers can place a star on the Hertzsprung-Russell diagram with a vertical error bar as thin as a few hundredths of a magnitude. The resulting age estimates differ by less than 100 million years, an interval that is a blink in the life of a star, yet crucial for understanding the chronology of planet formation. The laboratory of the sky is now quieter, the noise floor lowered to a level where even the faintest tremor can be heard. I sit at my desk, eyes on a screen showing a scatter plot of parallax versus magnitude, and notice a tiny clustering of points near a declination of plus 12 degrees. The points sit just a fraction above the formal error line, suggesting a residual systematic that aligns with the orientation of one of Gaia's CCD rows. It's a reminder that the instrument still carries the imprint of its own geometry, even after years of calibration. The parsec, a little over 3 light-years, is a ruler that turns imagination into ledger. When I write the numbers, the cold of the data feels heavier than the vacuum outside. A spacecraft that could cruise at 99% of light speed would cross 1 parsec in a little more than 3 years. The math is simple, the reality is not. Light time still drags, and the engine must keep pushing against an ever-present drag of photon pressure. Energy in this context is not a metaphor. To accelerate a kilogram to that speed, you need roughly 300 terajoules per parsec. That is the energy stored in a few hundred tons of gasoline, compressed into a single pulse. I find it hard to picture a battery that can hold that without melting. Breakthrough Starshot offers a different angle. Tiny sails, a few grams, pushed by a ground-based laser array, could reach a fraction of light speed. The concept folds the massive energy requirement into a brief, intense flash. The sail itself feels like a grain of sand trembling under a sudden heat. The laser has to stay focused across a distance measured in millions of kilometers. Any wobble becomes a blur and the sail slips into the dark. The engineering tolerances are tighter than the grain of sand I just mentioned. It does not quite make sense when you say it aloud. A 100 gigawatt beam aimed at a sail 3 meters across, 20 light seconds away. Even if the sail survives launch, the voyage will last decades. The probe will drift past its target, sending back a handful of photons that must cross the void to reach us. The signal is a whisper of electrons in a sea of noise. The receiving dish on Earth will feel the faint tug of those photons like a distant drumbeat. Human crews would face a different set of constraints. A multi-year voyage at near light speed means a life lived in a capsule that never feels the pull of gravity. The body loses bone density. The mind loses the sense of day and night. Psychological strain builds in a way that cannot be measured by a spectrometer. We can simulate isolation in Antarctic stations, but the isolation of a parsec-long trip adds a layer of temporal dislocation. You leave Earth at a certain calendar date, but you return to a world that has moved forward by years you never experienced. The calendar becomes a strange artifact, a grain of sand that has slipped through an hourglass you cannot see. Physics puts hard limits on how fast we can go. The relativistic mass increase means that each additional percent of speed costs disproportionately more energy. At 99.9% of light speed, the fuel requirement climbs faster than any rocket we have built. The laws do not bend. They simply remind us of the cold arithmetic. If we accept those limits, mission planning becomes a matter of balancing distance, speed, and payload. A gram-scale probe can be launched more often, each with a narrow focus. A larger vessel must accept a slower cruise or a massive energy infrastructure. The parsec forces us to choose between breadth and depth. The cost per parsec, when expressed in megawatts years, looks like a budget line on a spreadsheet. It is a number that sits on a page, indifferent to the poetry of stars. Yet that number determines whether a mission is written into a grant proposal or left as a thought experiment. Radiation is another unavoidable factor. At near light speed, the interstellar medium becomes a stream of high-energy particles. The hull must act like a shield, absorbing impacts that would feel like tiny meteors hitting a windshield at Mach 10. The material choice feels like a trade between weight and resilience, a familiar dilemma in any lab notebook. Thermal management also becomes a puzzle. The spacecraft's front face absorbs photons, heating it like a blacksmith's anvil. The back face cools into the cold of space, a temperature gradient that could crack brittle materials. The engineers must design heat pipes that work in a vacuum where convection does not exist. Navigation across a parsec relies on distant beacons, pulsars, quasars, or artificial laser markers. The spacecraft's sensors must lock onto these points with a precision that feels like feeling for a needle in a haystack using only a whisper of light. A miscalculation of even a few micro-arcseconds can shift the trajectory by millions of kilometers. Fuel storage adds another layer of weight. Cryogenic hydrogen, if used, must stay colder than liquid nitrogen, and any boil off is a loss of mass that cannot be recovered. The tanks themselves become a source of vibration, a low hum that can interfere with delicate instruments. The design feels like trying to balance a scale with one side made of ice. The parsec also frames our expectations about what is realistic. A mission that promises to reach Alpha Centauri in a decade must confront the fact that even a perfect laser sail would need a power plant the size of a small city. The numbers pull the dream back onto the workbench. In contrast, a slower, multi-decade probe can afford a more modest propulsion system, but then the crew, or the instruments, must endure a longer exposure to isolation. The psychological load is a weight that does not appear in a mass budget, yet it is as real as any kilogram of payload. We do not really know how the human mind copes with a lifetime spent in a windowless tube, watching distant stars drift by at a rate that feels both fast and slow. The only data we have come from submarines and polar stations, where the horizon never changes. That data feels thin when stretched across parsecs. The limits imposed by physics also dictate communication latency. A message sent from a probe at 1 parsec takes 3 years to arrive. Any command must be issued without expectation of a timely response. The spacecraft must be autonomous, making decisions on its own, like a lone scientist in a sealed lab. Autonomy requires onboard AI that can diagnose failures, reconfigure power, and adjust trajectory. The software must be robust against radiation-induced bit flips, each flip a tiny grain of sand that could tip the balance of a critical calculation. Testing such systems feels like trying to predict the exact pattern of rain in a desert. Even the simplest maneuver, rotating the sail to change orientation, requires precise timing. A misfire could send the craft off course by a fraction of a degree, which translates into a miss by thousands of kilometers at the target. The control loops are tight, the margins razor thin. If we look at the energy per parsec, the numbers suggest that a fleet of tiny probes could collectively explore many nearby stars, each sending back a trickle of data. The aggregate picture would be richer than a single, massive mission, but the data streams would be faint, like hearing a distant wind through a wall. The parsec, then, is not just a distance. It is a scale that forces us to confront the weight of each kilogram, the cold of each joule, and the silence of each photon that travels across it. It makes the engineering spreadsheet feel like a map of a desert, each cell a dune of possibility. I sometimes stare at the equation for relativistic kinetic energy and hear the faint clink of metal against metal, the sound of a hammer striking an anvil. It is a reminder that even the most abstract numbers have a tactile side. The parsec turns that clink into a reverberation that lasts years. At the end of a day spent in the lab, the most concrete thing I can hold is a small piece of carbon fiber, its surface feeling like the grain of a wooden board. It will one day be part of a sail that may cross a parsec. The texture stays with me, a reminder that the distance is measured in more than light years. I have spent most of my career writing down numbers that sit between us and the distant lights we point our telescopes at. The act of assigning a length to that emptiness feels oddly personal, as if we are trying to name a breath that belongs to someone else. When the first astronomers tried to pin down the distance to a nearby star, they were not just measuring a span of space. They were reaching for a place in a larger picture that stretches far beyond any single instrument. The link between distance and time is the most stubborn thread in that picture. Light, that relentless messenger, carries with it a built-in clock. Every parsec we quote is a reminder that the photons we catch left their source years, decades, even millennia ago. I find it hard to picture a star whose light has been traveling for 300,000 years, yet we still label its separation in a unit that feels almost absurdly small. The paradox is that the farther we look, the more we are forced to think in terms of ages rather than meters. That age-based perspective matters when we ask whether anything out there might share our chemistry. The search for life hinges on a simple arithmetic. We need to know how far a planet sits from its sun and how far that sun sits from us. Without a reliable ladder of distances, any estimate of surface temperature or atmospheric composition becomes a guesswork exercise. The habitability of a world is tied to the amount of stellar energy it receives, and that energy is a function of the inverse square of the distance. If our distance scale is off by a few percent, the temperature calculation can swing by tens of degrees, enough to push a planet out of the narrow band where liquid water could exist. Even with our best models, there are gaps that stubbornly refuse to close. The distances to many of the faint, red dwarfs that dominate the stellar census remain uncertain by more than 10%. Those are precisely the stars that host the majority of the small planets we can now detect. We don't really know how many of those worlds sit in the narrow band where water might linger. The uncertainty in distance propagates through every subsequent inference we make about their atmospheres, their potential biosignatures, and even the likelihood that they could ever be visited by a probe. The act of measuring also forces us to confront our own limits. Parallax, the tiny wobble of a nearby star against a backdrop of distant ones, is the most direct method we have. Yet the wobble is often less than 1,000th of an arcsecond, an angle smaller than the width of a human hair seen from several kilometers away. I sometimes stare at the data tables and feel the weight of that minuscule shift, and I admit it doesn't quite make sense when you say it aloud. The numbers are precise, but the physical sensation of such a motion is almost intangible. When we step beyond parallax, we rely on a chain of indirect indicators: Cepheid variables, supernovae, red shift measurements. Each link adds a layer of assumption, a potential source of error. The whole structure resembles a set of stacked plates. A slight tilt at the base can tip the whole thing. Yet we keep stacking because without a coherent distance framework, the story we tell about the universe would fall apart at the seams. Looking ahead, the next generation of space-based observatories promises to tighten those uncertainties. Instruments designed to measure stellar positions with micro-arcsecond precision will turn the current fog into something more like a thin veil. That will not only sharpen our estimates of where planets lie, but also refine the timing of events we observe across the galaxy: supernova explosions, gravitational wave signals, the flicker of distant quasars. In that sense, distance measurement is a kind of scaffolding that supports every other piece of astronomical inference. There is also a philosophical pull that I can't ignore. When we assign a number to a stretch of emptiness, we are, in a quiet way, asserting that the universe is something we can grasp, even if only partially. The act of naming a parsec is a reminder that we are not merely passive observers. We are participants in a dialogue that stretches across light years. It is a modest claim, but it carries a weight that feels almost ceremonial, a small, steady beat in the background of our larger attempts to locate ourselves. I sometimes wonder whether future generations will look back at our distance tables the way we now glance at the old charts of the 19th century. Will they see a clumsy first step, or a necessary foundation that allowed them to build something far more precise? The answer, I suspect, will lie in the details we leave behind. The exact value we recorded for the parallax of a dim star, the error bar we attached to a supernova's luminosity, the footnote about an unexplained drift in a data set. Those minutiae will become the clues that future scientists use to trace the evolution of our measuring practices. For now, the work feels both endless and essential. Every time we refine a distance, we tighten the knot that binds time, energy, and possibility together. The knot does not disappear, it simply becomes a little less tangled. And in that incremental tightening, there is a quiet satisfaction that comes from knowing a little more about the scale of the place we occupy. The parallax of Barnard's star shifts by barely half an arcsecond each year, a wobble you can barely see even with the best lenses.